And probably now we have more or less a final result. Now the problem is to use, in some sense, multiscale reduction and apply it, which was a technique introduced, very well introduced by Calogero and many other peoples. Later, Calogero and Leckhaus, firstly, and on the case of equation defined on a lattice. Now, so as somehow I will give some introduction on the multiscale analysis on simple examples, continuous examples, and then I will apply this to the case of discrete equations. So the multiscale analysis is a perturbation technique for constructing uniformly valid approximation to solution of system depending on a small parameter, and the non-uniformity arises from circularity, and we cancel that by requiring that, and that provide conditions. Now, the circularity which corresponds to unbound growth with time. The simple example is the damped harmonic oscillator, which where epsilon is a small parameter, is the damping, and we know that we have an exact solution which depends on scales of order 1 over epsilon, in both for the amplitude decrease and for the frequency shift. Now, if we look for a solution depending on slow variables like T1 is epsilon t, T2 is epsilon squared t, and so on, then the derivative can be written in terms of the new variable T1, T2, which are supposed independent, and we can look for a solution of our damped harmonic oscillator in terms depending on the vector t and on epsilon, given in this form, it's power series of epsilon. And then we have a series of equations, a cascade of equations which we solve. So at order epsilon 0, we have just the pure harmonic oscillator, whose solution, of course, is given here, where, however, the function a and b depends on the slow times, that is T1, T2, etc. Now, at order epsilon 1, we have a coupling of x1, the solution, an differential equation for x1, which depends on time. And if I solve it directly, which I can do, I will have terms which grows with time. So these are unbound. This unbound growth is non-physical, correspond to what are secular terms. So to cancel it, we require that the function a and b satisfy this equation so that this term disappears. So we choose a and b to satisfy these two equations, so it has this form, and dependence with T1 is fixed, but of course T2, T3, etc., B1 will depend, and A1 will depend on the other variables. So if we now get the solution at order epsilon square, we get this expression, which is exactly the solution, the series expansion of the exact solutions. So this is a way, in some sense, to get by a perturbation technique a solution, the main part of a solution which may have now this multiscale analysis has been used as a perturbation technique for testing integrability of given nonlinear system, mainly the work, as I told before, by Calogero and Leckhaus, and then later applied by De Gasperis, Manakov, and Santini as a testing integrability technique. And one of the results of this is the Gasperis-Procesi equation, which was obtained originally in this way. There is work also by Kodama and Mikhailov, written in normal forms, which is similar to this perturbation technique. Now, what is one of the results of this in this approach are given by work by Zakharov and Kuznetsov for partial differential equation. Also here, all this work are for partial differential equation in which they show that integrability is maintained in the reduction process. And if you start from an equation which has a Lax pair, you go down to a reduced equation which has also a Lax pair. As an example, also trivial example, and well known is the case of the KdV, and contained in the work by Zakharov and Kuznetsov, is the case of the KdV equation. So we start from the KdV. We assume a solution which depends on multi-timing. There is a wave solutions. So it's a perturbation of a solution of these kinds. And then we have slow variables, which are as low x and a multiple set of slow time. Now, if we have to impose, of course, KdV we assume to be real, then we have to impose a reality condition in the expansions. And then of course, we'll have the space and time derivative will be transformed in this way as we take that psi, T1, T2 are all independent variables. Then at lowest order, we get the dispersion relations. At the higher order, we get this for epsilon square. We have, in the case for the zero harmonics and first harmonic, we get these two equations whose solution is given here. And then for the second harmonic, we have a relation between the first component and the second one. If we go to the order epsilon cube, for the zero harmonic, we have this equation. Now, here we have to require some no circularity conditions. So here, if I look at these equations, then if I have a problem because I have to, I will have some, the solution will give some wave breaking, so which break the kind of solution, the continuity of the solution I want. And so this implies that I have to have these two conditions, and if I go to the first harmonic, I get that the right-hand side solves the homogeneous equation, so I have still circularity, and so I have to request that the left-hand side and the right-hand side has to be zero independently, and on the right-hand side, what I get a nonlinear Schrödinger equation. So what it tells me that if I start from a KdV, which is an integrable equation, I'll go by multiscale expansion to a nonlinear Schrödinger equation, which is also integrable. Now, the fact is that nonlinear Schrödinger is a universal system in a certain sense. When I require the multiscale reduction of whole classes of equation, I get as first order, I get the nonlinear Schrödinger. Now, the condition to get a real test, this is I get for many equations, so it doesn't really limit a lot our conditions on integrability. So to go to really make an integrability test, we have to consider higher order terms beyond the nonlinear Schrödinger equation, and this is mainly due to the work of the Gasperis, Manakov, and Santini. The main proposition is that if an equation is integrable, that under a multiscale expansion, the various functions of the coefficients of the expansion has to satisfy a set of equations for the various times, Tn, and these k are the n flow of a hierarchy of integrable equations. So you have to require that this is the resulting equation belongs to a hierarchy, and moreover, you have that, you define an operator M, which is determined in terms of a Fléchet derivative of the hierarchy of equations in the direction V. And then we have that this linear operator is a combination of non-homogeneous forcing terms, which are defined polynomial vector space and of a certain homogeneous degrees. So now the compatibility conditions, well, the fact that you have these equations for all order, this implies some compatibility condition, that is that mk applied on Gn should be Mn applied on Gk for k and n greater than 2. And this compatibility condition gives rise to some integrability condition, which are set of equations among the coefficients of the polynomial G, which of these polynomials, which has to be identically satisfied. Now, so this, the construction of these integrability conditions is done once for all, is cumbersome, but at the end you can use it to really prove integrability. Now, the Gasperis and Procesi introduced this definition that if the compatibility conditions are satisfied up to some index j greater than 2, our equation is asymptotically integrable of degree j. So the A3 integrability condition has been calculated by many people, both in the case of weakly dispersing nonlinear waves, that is, in terms of the KdV and potential KdV hierarchies, or in strongly dispersive nonlinear waves for the nonlinear Schrödinger hierarchy. What we did at the end is also to compute the A4 integrability condition for the NLS hierarchy. And the results are what I will present now in the following. So what I am doing, so we start from a multilinear quadratic equation, which is generically written here, which depends on 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16 parameters, and for a real function u on the lattice. And then we will look for solution for perturbation around the plane wave solution of the linear part, which is given here, the term of this form. Now, this implies that we need to have, so the linear dispersive solution is given whenever in these two cases, either I4 is I1 or I2 is I3 equal I2, whenever I1 different from I2. And this is what is called the class Q, we call class Q plus, or in the other case, Q minus. Now, we concentrate in this work on the class Q plus, and this is the class of equation. Now, this, of course, we have a 2 parameter less. Now, in this case, the dispersion relation is given here, and this implies that A1 must be different from I2 in modulus. Otherwise, this is become not possible. Then we classify the equation according to equivalent class, which is given by a subgroup of the Mobius transformation, and we seek solutions of this class. So there is a plane wave, and then there's a perturbation around the plane wave, depending on slow variables. We want a real solution, so we impose this condition of reality. So we have the parameter epsilon, which is a perturbation parameter, and then we introduce N1 is epsilon n, and Mj is epsilon to the Jm. So our slow space and slow time variables. Now, so we will take we'll consider Uj alpha, depending on the slope variables, to be a C infinity around this in the variable N1 and N1 and 2, so that we can expand the shift operator in terms of derivatives in the variable, in the slow variables, and then we can, of course, we will have an infinite. The equation will becomes an infinite differential equation, and then we can compare the result with respect to the hierarchy of the nonlinear Schrödinger. So at order epsilon cube and the alpha for the first harmonics, alpha equal 1, we get a nonlinear Schrödinger equation which coefficients rho 1 and rho 2. So these coefficients rho 1 and rho 2 are rational expressions of the parameter of Q plus and the coefficient and the cosinus k and sinus k. And these are independent. Cosine k, sin k is independent variables. So so the epsilon cube integrability conditions implies the fact that the imaginary part of rho 2 has to be 0. Otherwise, this is not a real nonlinear Schrödinger, the integrable nonlinear Schrödinger for any k. And this implies a system of 5 nonlinear algebraic relations between the parameter, which define 6 cases of equations. Now, if we go to the epsilon equal 4 integrability conditions, this we have an A2 integrability case, which is defined in terms of 2 constant. This, of course, corresponds to a higher order nonlinear Schrödinger, which is characterized by 2 parameters, A and B, which has to be real. Now, this requirement impose condition which reduce to two cases. So we can state the following theorem for the A2S integrability, that the only A2S integrable equation in our class are the one characterized by 9 free parameters, where the coefficients are given here, but is not particularly relevant in some sense, and the second one with A free parameters. And these are the conditions on the parameter. Now, if we go to the still higher order, to order epsilon to the fifth. We go over to a linearized forced nonlinear Schrödinger, and this here is a polynomial combination of 12 differential monomials in U1 and U2, which coefficients, which has a tau, which has a real and imaginary parts. And the request of integrability implies that we have 15 conditions. So the number of conditions increase every time that we are going higher in the expansions between the Rj and Ij. And this reduce this act on the parameter, and so we have a restriction which in this case give 5 cases which are given here. So these are the 3 integrable cases, invariant under restricted Mobius and disjoint that is not equivalent one to another. So these are the equations, and these equations contain already known integrable equations, but are more general, and they obtained by fixing parameter, we get known equations. For example, if I take S5, where it is? S5 is this one. Then if I fix the parameter zeta in this way, then if I do a canonical transformation, Mobius transformation, transform the parameter and so on, I get down to this equation, which depends only on one parameter epsilon, which is different from 0 and plus, which is the ratio of A1 and 2, the coefficients of the linear part, which should be different from 0 and plus or minus 1. Viallet showed that there is vanishing algebraic entropy in this case, and for epsilon equal 1/2, we show, Yamilov and myself showed that this has a 5-point generalized symmetry. And later I worked with Shimiterna, Ramani, and Grammatico showed that this is in some sense equivalent to a discrete sine-Gordon equation. Now we went higher, and this is the main result of our work, is that we went to the epsilon to the 6th integrability conditions, and we have what is called A4 integrability. We have, instead of 15, now we have 48 real relations, and what we get is that even with so many relations, which these relations do not fix anymore, all the equations that we had shown before pass these 48 integrability conditions. So, and by adding some further condition like exchange of n with m and transforming n into minus n, we have reduced the number of equations to 4, and our assumption is that these equations are integrable. These are this depends on one parameter, and this also depends on one parameter, epsilon. This was tau, and these other two depend on 3 parameters, and are given here. Now, the strange thing is that if we do these transformations, it is going from V to W using coefficients which depend on delta and the sign of epsilon. What we get is the case T3 and T4, they become this equation, which apart from the constant coefficients are known to be integrable. Well, our assumption is that integrable even with this coefficient. Now, well, what is the conclusion? So we have shown that the multiscale expansion, in some sense, applied when we apply it to discrete equation, is provide effectively a screening of is a test of integrability, which allow us to classify classes of integrable equation. And the work I presented was just in the case of U plus. This same procedure we have been carried out also for the linearizability, now also for the integrability. Now, what we have to do is to now analyze the resulting equation to show effectively that they are integrable, maybe by proving the fact that they have higher order symmetries. And also we have to go over to the Q minus case, which is a little more complicated because we have to, the equations at lowest order have to be considered, and they are a system of coupled equation. We don't get the kind of nonlinear Schrödinger, at least at the lowest order. Then, okay, we can do classification. We hope to be able to do classification on an autonomous case and extend the classification also to non-dispersive case. Okay, so thank you.
Are there any questions for this?
Hi, Decio. This is really a tour de force, isn't it?
Well, it took a lot of time.
I bet it did, yeah. Because these solvability conditions are really just expressions of the Fredholm alternative, is there a way that you could do it all in one go by having the linear stuff on one side and everything else on the other side, and then calculating the solvability conditions directly? Have you looked at that?
Well, I don't think so. It seems to be quite more complicated.
It's too complicated.
Yeah.
Okay.
Higher order symmetry means infinitely. Higher order symmetry means infinitely many, or
Well,
you mentioned higher order symmetries for integrable.
yeah. Well, like we did for some of the equations, some cases we did with Yamilov to show that at least 5 points symmetries, and maybe if you can find the recursive operator, go up to at infinity. Of course, in principle, this as the equation, as a differential, any discrete equation, as a differential equation is an infinite, as a differential equation of infinite order, you should go to infinite order in epsilon to get the proof directly. That, of course, you cannot do. So already to get to this order was somehow quite complicated. But still it's suggestive. The fact that at the last order we do have no condition on the parameter, this is suggestive the fact that you are already in asymptotics.
Are there any other questions? Okay, then let's thank Decio.